In this video, we're going to prove the basis representation theorem. So first, let's introduce some notation. We're going to say that b sub k of n is the number of representations of n to the base k. And if the theorem is true and there's only one representation, then we're going to set out to prove that this equals 1. So let's do it. So first, let's write n like this. Let's write n equals a naught k to the s, just like we've done before, plus a1 k to the s minus 1 plus dot 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 plus a to the s, a sub s minus t, k to the t. And you're going to notice this is a little bit different from how we wrote it back here. So here we wrote it like this, because here we included all the terms, all the coefficients, all the ai's. Even if they're 0, we left them in there. But in this representation, we're going to leave them out if they're 0. Which is why s minus t is basically the last term that is not 0. So we have this right now. We have this tool. And if we just take n minus 1, we're going to find the representation of n. We're going to find the representation of n minus 1 to the base k. So first we'll write it just as it is. Plus a1 k s minus 1 plus dot 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 plus a s minus t k to the t, simply minus a 1. And now we're going to do some algebraic manipulation, where we have a naught ks plus a1 ks minus 1 plus dot 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 plus a s minus t minus 1. And then we're going to have k to the t plus k to the t minus 1. So look at this, and we haven't really done anything, because here, if we expand these parentheses, it's going to be a sub s minus t k to the t, which is this, minus k to the t plus k to the t. So that's going to cancel out, and we're going to be left with a minus 1. We're just doing this because we want to show this in different form. And I need some more space. So, and then we're going to finally write this. We need to recognize something. So remember let's look at this term, k to the t minus 1. And then let's look back at our theorem number 1, which says that, remember, k to the n minus 1 over k minus 1 is equal to all this sum, and we're just going to rewrite that. So basically it's going to look something like equals a naught k to the s plus a1 k to the s minus 1 plus dot dot plus, and it's going to be a sub s minus t minus 1 k to the t plus, and then we're going to rewrite that. So it's going to look like the sum from j equals 0 of k to the j all the way to t minus 1, and that times k minus 1. So let's make it clear so we know what's going on. This term right here is the same as this term right here, because remember this, we know that k to the t minus 1 over k minus 1 equals this. So therefore, just rearranging our fraction a little bit, k to the t minus 1 equals k minus 1 times that whole sum. Okay, so we have basically shown right now that if n has a representation to the base k, then we can find one for n minus 1. That we have a method that shows if we have representation for n, that proves that the representation for n minus 1. And we've also proven that for each new representation, like let's say b sub k of n is some number like 2, let's say there's another representation, then that's going to yield a new representation of n minus 1. And that's enough to establish our inequality that b sub k of n is less than or equal to b sub k of n minus 1. And what we basically said, what this basically means right here, is there are more than or equal to representations of n minus 1 to the base k as there are representations of n to the base k, because each representation of n to the base k yields a new representation of n minus 1 to the base k. So there can never be less representations of n minus 1 to the base k. So let's keep this theorem in mind. And I think I need to get this paper. So I'll put this over here, and we'll just keep going. So now the rest of the theorem is fairly easy to prove. So first, let's just make a side note. This inequality right here even holds when b sub k of n is equal to 0 when there's no representations, because that means that b sub k of n minus 1 is also equal to 0, and 0 is less than or equal to 0. So we'll put that over there. And then we're going to finish this off. So basically what we've shown, since n minus 1 is less than n, we've shown that if a number is greater, it has less than or equal to representations as a number higher, as a number lower than it, sorry. So let's just, to prove my point, let's put in some numbers here. Let's say n equals 5, so then n minus 1 equals 4. So there are more than or equal to representations than of 4 than there are for 5. And now, let's visit that theorem that I promised we'd use. This one right here, k to the n is greater than n. So we know that k to the n is greater than n, and we know that greater numbers have less than or equal to representations. So we can establish that bk of k to the n is less than or equal to bk of n. But k to the n has at least one representation, at least one. And what is it? It's itself. Because k to the n is a representation in itself. Because remember how we wrote representations in the first place? We wrote them like this. So if we tried to write representation, it would just be a naught would be 0, s would be n. So it would just be a naught would equal 0, s would equal n, and we would just be left with k to the n, and all this other stuff would just be 0. So we know that b sub k of k to the n is at least 1. So it's greater than or equal to 1. And we know this is true. And we also know that b sub k of n is going to be less than or equal to b sub k of 1. Because remember, the lower the number in the parentheses gets, it is always greater than or equal to a number that is higher than it. And n, remember, the lowest it can be is 1, because we established in the very first place, that, where'd it go? Let n be any positive integer. So we know that this is less than or equal to b to the k, b sub k of 1. And the last thing we need to show, we know that b sub k of 1 is equal to 1, because 1 has only one representation to the base k. And let's show that what it is. So remember our definition right here. So the only way to write 1 in any base, so how do we do this? We're going to have s is going to have to be 0, and a naught is going to have to be 1, because that's the only possible way we can do it. Because remember, a naught can't be 0. Also, all these other coefficients, these ai's are going to have to be equal to 0. So in this case, a naught equals 1, and s equals 0. So then we have 1 times k to the 0, which is 1. And that's the only representation. So let's just go over, we basically proved it now, but we have to figure out what we wrote in this huge inequality. We've shown that, looking at the extremes of this, we've basically shown that this is what we're interested in right now, b sub k of n. We've shown that b sub k of n is less than or equal to 1, and is also greater than or equal to 1. And that is enough to prove that b sub k of n equals 1, because we've sandwiched it, essentially, between the same number. And so it only has one choice that it can possibly be. So we've proven the basis representation theorem, which many think is a pretty obvious theorem, but in number theory we have to prove everything from the start. So it's a pretty good result.